Alrighty, in this video, we're going to give a quick overview of the different phases of bacterial growth. So make sure you know that this is bacterial growth. Growth for other organisms is slightly different. And we're just going to talk about what those phases are, pop up some equations to show you what's going on in each of those phases. And then we'll talk about the equations a little bit more in the next video and in class. So there are four phases of bacterial growth. There's the lag phase, the exponential phase, the stationary phase, and the death phase. And sometimes death phase is called endogenous decay, depending on the textbook or the manual that you use for design. And a little fun fact question on the bottom, what do we call the shape of a bacterial growth curve? This is a sigmoidal or sigmoidal curve when we do bacteria curves, because it looks like an S, sigma. So let's start with lag phase. So in lag phase, the growth rate is pretty close to 0. Basically, the cell is trying to adapt to cultural conditions, like what's in the culture. So the bacteria is trying to produce enough messenger RNA to produce enough proteins for growth. So the cell is really trying to get itself set up. The conditions are probably pretty good if we're growing in culture, and the cell has adapted to the fact that it has conditions for growth. So then the cell response will be that it starts to move that messenger RNA and proteins to the ribosomes to start producing what's needed for that growth metabolism. Generally, they also try to dilute any exoenzymes that are outside of the cell. And how fast that lag phase is inoculum dependent. So it's dependent on how the cell was added to the culture and how the cell was cultured itself. So cells that are primed to grow in a specific new media will have a shorter lag phase, right? They'll get growing really, really fast. So if the media is good for the organisms and they're primed and ready to go, they have exactly what they need to grow, the lag phase is going to be short. If the inoculum is larger, so the sample basically is larger that gets plated, it might have a shorter lag phase occasionally too. So what this, that should be, no, a longer lag phase, excuse me. If it has so there's some slight issues with the slides now that I look at it. If the inoculum is larger, they'll have a longer phase. So think of that as putting too much of your sample on your Petri dishes, right? It's going to take longer for that sample to diffuse into the nutrients. So just make that correction on your slides that if the inoculum is larger, it's going to have a longer growth phase. Sorry for that mistake on my slides. And that's all that graph is showing you on the other side of the screen. So that's the lag phase. It's not all that fun. The fun phase is the exponential phase. So bacteria, remember, reproduce by binary fission, cell division, right? So as the cell divides, if the conditions are optimal for growth, we have exponential growth because we have a doubling effect happening. So we double the number of cell units per time, and that is the most rapid growth that is possible in a true batch system. So we have exponential cell division. Each cell division results in a doubling of the number of cells. At low cell numbers, the increase is not very large, but after a few generations, it gets very, very big. So if we take a look at the slide, first generation is at the top. Second generation has what we call daughter cells. And the third generation only has 4. But by the time we get to the 4th and the 5th, and then the 6th generation, because of exponential growth, the cell numbers are increasing exponentially and explosively here. In exponential phase, we express this mathematically by saying that x, which is the concentrations after a given time, is equal to 2 to the nth times x sub 0. So x sub 0 is the initial concentration of cells, and n is the number of generations or cell divisions that have occurred. So we can also rewrite this in terms of n to figure out the number of generations. So this equation right here at the very bottom is just rearranging this equation up top so that 0.693 comes from taking the natural log of related to 2 to move things around. So it's exponential growth, right? And we know that it's base 2, so that's why there's a 2 to the n there. And basically what you have at a final time is related to how many generations have happened times whatever initial concentration of cells you had. So if we rearrange, we get that equation we just talked about, right? But we can also rearrange the equation that we first saw to be a little bit different. So we can say the natural log of the cell concentration at a given time is equal to the number of generations times natural log of 2 plus the natural log of the initial cells. So we manipulate this equation to find different things depending on what we're looking for. Most of the time we're probably looking for x, but on occasion we will look for the number of generations. Sometimes we don't know the initial cell concentration, but the final cell concentration is easy to find. So we can use that to backtrack to the initial concentration as well. In exponential phase, we can have a couple different terms. So this is a terminology slide. Balanced growth happens when we stay in the exponential or logarithmic phase. So if we want to keep cells growing, we are going to try and keep them in that exponential or logarithmic phase of the graph that you saw in the last video. Generation time is a term that we used for the time that is needed for cell doubling. So doubling the amount of cells that's there in the system. The specific growth rate is slightly different. It's the maximum growth rate that can be achieved with whatever environmental conditions are present. So in reality, right, we're not always going to have the perfect balanced growth rate. We're going to have a specific growth rate that is based on whatever substrate is there, and then whatever could be building up as a result of cell production in a system. So substrate, remember, is food or nutrients. As that substrate runs out, we can't have exponential growth anymore. So once substrate is gone, it's going to limit how fast that exponential phase can go, and we might start to get into the next phases. The other thing that can happen is when cells reproduce, there can be a buildup of toxic byproducts, so things that cells are also producing as a part of their metabolism that build up, that limit the ability of cells to keep reproducing. And so if either of these things happen, cells are going to leave the exponential phase and that specific growth rate will decrease. So substrate and byproducts are the two things that are going to kind of slow down that specific growth rate. Specific growth rate has a formula, and it's an it's differential. So a dx dt is the change of number of cells at a specific time, and then mu, this Greek letter mu, is the specific growth rate and it's represented, in units in terms of reciprocal hours, so 1/hours. So what we have is dx dt equals the specific growth rate times the concentration. So if we integrate that, we get x over x naught equals e to the mu t. Just couldn't see my writing there. Mu t. And if we took the natural log of both sides, we could find what the specific rate is actually equal to. So specific growth rate is important to us as environmental engineers, specifically because we might want to know how an organism grows the best in a reactor. So growing organisms in a reactor is actually really important for wastewater treatment. We want an optimal growth rate for specific organisms of concern. So understanding what the specific growth rate of a specific microorganism is really important to optimizing specific types of reactor processes in wastewater treatment. Third phase is called the stationary phase. This is when there is no net state of growth. So dx dt is equal to 0. There's no change in the number of cells over time. So this is basically the plateau on top of that sigmoidal curve. So no net growth. The number of new cells that are being generated is balanced by the number that's dying, because cells are going to die as well in these systems, right? They don't just keep growing. They don't get bigger and bigger. They die over time. We can move to stationary phase if we move out of exponential phase when we have that substrate become limiting. So when we don't have enough nutrients for everybody, that's a limiting case. It's going to pull us out of exponential into stationary phase. We can have in stationary phase this weird thing called endogenous metabolism, and that's where dead cells are recycled to provide a source of nutrients for cells. So there can be some metabolic activity in stationary phase due to growing cells metabolizing the byproducts of dead cells. That's endogenous metabolism. So something can be happening in stationary phase. It's not that things are not growing. It's that the rate of growth is being balanced by the rate of death, right? So if you did mass balances with me, right, your inputs and your outputs are balancing. Your generation, your consumption is balancing. There's no accumulation in the system, right? And this is a plateau in growth. Last phase is called the death phase or endogenous decay, and it's a net loss, right? So this would mean consumption or output is greater than input or generation in a mass balance, right? It's a net loss of culturable cells, so the number of new cells that's being generated is less than the number dying. So that's that last part of the graph. And the key thing right here is that it's not that new cells are not growing. There are new cells being produced, but they're being outpaced by the number of cells that are growing. It could be exponential, the death phase, but it's not as fast as the actual exponential phase itself. And then one thing that I do want to point out on this slide is that we have optical density in red, but we also have turbidity being measured as well. And turbidity is another measure for optical density. So why would the turbidity curve not be showing the death phase? Well, part of the reason that it doesn't actually show the death phase is that the cells are still there. We just can't use turbidity to figure out whether cells are alive or not. Right? So cells are still going to be there. They're still going to be part of the turbidity reading, but it's hard to figure out if cells are alive or dead via turbidity readings. Last thing with the death phase is we can use a very, very similar equation to our exponential phase with our specific growth rates, but we have a K sub D here and we have a negative sign, and that's important. And K sub D is what we call the specific death rate. And this phase, right, is characterized by that net loss of cells. So we have that minus K sub D. So individual cells can be metabolizing and dividing, in the death phase, but overall there's a net loss of cells. And I'll leave you with the question, why might we be losing cells in a system? So think about that. That's going to conclude us for the growth phases, and we'll move on to growth equations in the next little pre-lecture.